the global economy moves by water. Every day, tens of thousands of massive steel hulls carve through the ocean, requiring immense kinetic energy generated almost entirely by burning heavy fossil fuels. The International Maritime Organization has issued MEPC 80/2023. This mandate requires the shipping industry to reach net zero greenhouse gas emissions by the year 2050. This timeline tracks the regulatory roadmap. Look right. The progression from 2023 regulations to the 2030 interim milestone is incredibly steep. Within that window, the mandate requires a 5 to 10% uptake of zero-emission fuels. The industry is currently missing this trajectory. Progress is stalled by intersecting barriers. Capital expenditures fall short for advanced technology. Global bunkering infrastructure for alternative fuels does not exist at scale. And regional policies enforce contradictory compliance standards, making international routing a logistical liability. At a scale of $40 billion, an industry-wide attempt to adopt these technologies simultaneously creates impossible capital requirements and systemic operational instability. A transition this complex demands a localized, iterative strategy. The structural framework required to achieve this localization is the Green Digital Shipping Corridor. A green digital shipping corridor is a designated end-to-end maritime route connecting specific ports. It operates as an isolated ecosystem to test, prove, and scale zero-emission fuels and smart technologies in a controlled environment. This diagram outlines the corridor framework, highlighting the Liverpool-Belfast route. This specific geographic artery is currently acting as a pilot model, testing the integration of alternative fuels alongside commercial shore power. These routes function effectively because they force the simultaneous convergence of three required pillars: decarbonization, digitalization, and the human element. They operate as active financial mechanisms. By isolating the variables, stakeholders can de-risk their capital investments and prove operational viability before committing to a global rollout. The foundation of the corridor is its physical layer, replacing legacy fossil fuels with zero-emission alternatives. Green ammonia and hydrogen have now rapidly emerged as the primary zero-carbon candidates to power these maritime routes. These chemical alternatives present a direct physics problem: lower energy density. To generate the same thrust, vessels must carry significantly larger volumes of fuel. Expanding this internal storage directly cannibalizes the ship's hold. Every cubic meter of fuel is subtracted from profitable payload space. Storing these volatile elements also requires extreme engineering. Hydrogen demands cryogenic cooling, and ammonia requires heavily pressurized tanks to remain stable at sea. The specialized port infrastructure needed to safely bunker and transfer these hazardous fuels currently exists at only a fraction of global terminals. Because supply and infrastructure are scarce, operating on green fuels currently drives up a vessel's operating costs by 30 to 50% per voyage. That operating penalty comes on top of massive capital expenditures. Retrofitting a single legacy vessel to safely handle these new propulsion systems can cost up to $6 million. Physical retrofitting and green fuel adoption cannot survive in isolation. Without a secondary mechanism to drastically cut operational waste and recover those losses, the physical transition is financially unsustainable. To fund the decarbonization process, the industry relies on the double D trend, pairing decarbonization directly with digitalization. This shift to Shipping 4.0 turns the vessel into a floating data center. Every engine component and atmospheric sensor becomes a primary source of operational intelligence used to fund the green transition. AI-driven navigation systems continuously ingest real-time meteorological data and vessel hydrodynamics. The algorithms process these variables to compute optimal routes and adjust speed profiles, stripping away excess fuel consumption mile by mile. The data generated at sea flows directly into the Smart Port ecosystem waiting on land. This graphic maps the self-optimizing loop driving smart terminals. IoT data feeds the perception layer, allowing AI to execute decisions like automated berth scheduling. Managing this requires a robust connectivity backbone. Private 5G networks and edge processing eliminate latency, ensuring instructions reach machinery in milliseconds. This zero-latency environment coordinates autonomous carriers and robotic trucks. They move in synchronized patterns across the terminal floor, eliminating idle engine time. The digital network also serves as the primary safety net. Networked IoT sensors run continuous condition monitoring, instantly detecting pressure anomalies or toxic leaks near the ammonia storage tanks. When intelligent scheduling meets automated cargo handling, a vessel's time spent idling in port drops by up to 25%. This chart highlights the projected financial impact. By optimizing routes and eliminating wait times, digital integration can yield up to a 46% reduction in fuel and energy management costs. Inside a corridor, these digital efficiencies generate the capital required to offset the severe hardware and fuel penalties of decarbonization, yet both the physical and digital layers depend entirely on the third, most vulnerable pillar, the human capital required to operate these systems. This diagram highlights the industry's demographic crisis. By the end of 2026, the maritime sector is projected to face a shortage of nearly 90,000 certified officers. To meet the net zero timeline, up to 800,000 existing seafarers will require intense, specialized upskilling just to safely manage hazardous materials like liquid hydrogen and pressurized ammonia. The nature of maritime work is changing. The cognitive load is shifting away from manual mechanical tasks toward complex interdisciplinary data analysis and human-machine interaction. Connecting physical propulsion and steering systems to external digital networks exposes vessels to severe operational technology cyber risks, where a data breach can disable physical machinery. Navigating these threats requires a new operational profile. This diagram maps the necessary skill sets. Seafarers must possess overlapping competencies in digital analysis, automation oversight, and rigorous safety protocols to execute continuous improvement. Achieving the 2050 net zero targets is impossible if the industry treats technology as a siloed upgrade. The hardware and software are useless without an upskilled, specialized workforce to integrate them. Stepping back from the mechanics of a single route reveals the macro requirement for global stakeholder alignment. A green digital shipping corridor forces the creation of a closed-loop ecosystem. Port authorities, charterers, and regulators must share verified, immutable data to make the route function. This chart maps that exact value chain. Live sensor data from the fleet dictates green energy production schedules at the port, which simultaneously feeds into automated compliance reporting for the regulators. The strategic goal is to build these self-contained corridors, refine their efficiency, and then link them together, standardizing and scaling the infrastructure across the globe. Approaching the 2050 mandate with piecemeal, uncoordinated technological upgrades will not work against the physical and financial realities of maritime trade. The required evolution demands all three elements working in tandem. Decarbonization provides the physics, digitalization provides the economics, and the human element provides execution. To survive the current regulatory window, the maritime supply chain must stop operating as a loose network of independent ships. It has to act as a single, fully integrated cyber-physical system.